If we zoom down to the molecular level and look at a system that consists of gaseous water molecules, we'll see that the water molecules are zooming around in the system, and every once in a while they'll collide with one another and go off in a different direction. If we look very, very closely, we'll find that not all the gas molecules are going at the same velocity. If we set about to count the number of molecules that are going at each particular velocity that's possible, so all possible velocities or all possible speeds, we'll find that none of the molecules are going at zero velocity. So when we have zero velocity, we have no molecules going at zero velocity. In other words, all molecules are always moving. Likewise, clear out here at infinity, we have no molecules that have an infinite velocity. And so we have no molecules at zero velocity, we have no molecules at an infinite velocity, but clearly we have velocities that are between 0 and infinity. So our distribution, our number of molecules that have a particular velocity, is going to have to increase and then come back down and decrease back down to 0 at infinity. And so in fact, what we'll find is that our distribution is going to look something like this. This is called the Maxwell-Boltzmann distribution of speeds or velocities for molecules in a system. Note that if molecules are going faster, then they will collide with a larger kinetic energy. Remember that the kinetic energy of a molecule is 1/2 times its mass times its velocity squared. And so the faster the molecules are going, the larger the energy of the collision. And so if we think about this distribution in terms of collision energies, we'll see the same kind of distribution where we have no collisions with zero energy, no collisions with an infinite amount of energy, but collisions that occur at all the energies in between, but we will have more collisions at some energies than at other energies. So if we now look at the number of collisions that have a particular energy, we'll see that same distribution that we saw for velocities. What we will note is that when the system is relatively cold, has a lower temperature, that the distribution will be skewed, will be at lower energies. So as I raise the temperature, my molecules go faster and faster and faster, and so I have more molecules that have collision energies that are at higher collision energies because they're going faster. And so at higher temperatures, I expect to see this distribution spread out and shift to larger collision energies. This is important because when we have a reaction, the collision has to happen with enough energy for that reaction to occur. And the energy that is required for the reaction to occur is something that we call the activation energy, and we give it the symbol E sub A. So this activation energy is a threshold energy that is required for a reaction to occur. And so only molecules that have collision energies that are above the activation energy for the reaction are even going to be able to react at all. And so you can see that at these lower temperatures, we only have this fraction of molecules that have enough energy to react. But if we look at a higher temperature, we now have a much larger fraction of molecules that will have enough energy to react. And so we would expect reactions to go faster at higher temperatures than they do at lower temperatures. It turns out that the fraction with enough energy, so energies greater than the activation energy, that fraction is equal to the exponential of minus the activation energy divided by the gas constant times the temperature in Kelvin.